And so now we come to standing waves. Standing waves. What are standing waves? Well, up to this point, we've talked about like a pulse of a wave that is reflected from a fixed end. And we've already done that. But what if somebody's consistently, whipping the string to where you have simple harmonic motion that's going and it's reflecting off a fixed end, but it's doing it in a regular kind of pattern. What's going to happen is a standing wave is going to set up. It's going to be a wave where there's a consistent superposition of a regular incident wave with its reflection. And so, you're going to have some up and down motion at particular points, but it's not going to travel like this. The wave is not going to be, it's not a traveling wave. It looks like it's not moving from side to side. It is moving at some points up and down. I don't know, I'm thinking of some old, movies I've seen where, there's kind of a computer talking and the wave is going up and down. Anyway, maybe you've never seen anything like that. So the wave doesn't seem to be moving back and forth, but it is kind of moving up and down. And that's because there's going to be a consistent overlapping superposition. Remember, if you have a position and then you have a superposition, it's something on top of something else. That's the adding together of the waves. And so if it's a consistent source of harmonic motion, it's going to be a consistent, canceling out and adding to of the wave. Nodes are points where it's always going to be zero. So there's going to be certain points on a standing wave where it's always zero. No matter the in-between parts may be going up and down sinusoidally, but the node will be zero in between. And so you're going to have this, thing, but it's going to be zero always at certain points, and those are called the nodes. Meanwhile, the antinodes are the points between the nodes that are going, up and down. Okay, so nodes, zero, antinodes, midway between them. So let's talk about some terms that we use when we're talking about superposition. So when the superposition of two waves cancels each other out, whether entirely, as at a node, or to some degree, that's called destructive interference. So when the two waves cancel each other out to some extent, that is the wave going and the wave returning, that's going to be destructive interference. But when the two waves add the going and coming, that's going to be called constructive interference. So destructive interference is when the two waves are canceling each other's out to some extent, and constructive is when they're going to be adding to each other to some extent. Now the distance between two nodes, or the distance between two antinodes, again, nodes are where it's zero, the distance between two nodes is going to be half of a wavelength. And the symbol we use for wavelength is a Greek L, which is a lambda. That's what this thing right here is. That's a lambda. It's a Greek L. So half of a lambda, half of a wavelength, is going to be the distance between the two zeros, the nodes, or the distance between two antinodes between the nodes, okay? And then lastly, if you think about it, you have an amplitude of the wave. When they're perfectly constructing with each other, that is, we have total construction. We have this wave and this wave are adding to each other. Obviously, the maximum amplitude is going to be twice the amplitude of the original, kind of wave. Okay, now that we've got that out of the way, let's talk about an equation. Let's do the math. What is the wave function? What is the wave equation for a standing wave? Well, there it is. It's going to be the amplitude of the standing wave, which we know is twice the regular amplitude, twice the incident amplitude. So the amplitude of the standing wave, or 2a, sine of kx times the sine of omega t. So this is, again, is a function that involves both an x and a t. Okay, how do they get that? Well, they actually do it by taking the regular wave equation, if you remember, is y of x and t equals the amplitude times the cosine of kx minus omega t. And what they did is they just added that twice. The one is moving in the opposite direction, so you have to put a negative on it, and so forth. But then they used a trig equation. Now, if you have a good trigonometry class, your trig professor is going to have you memorize some kind of formulas, some identities. And so Young and Freedman, for example, they apply a certain trig equation, and this is what they come up with. Again, more important to be able to use the equation to be able to derive it. But this is basically an equation, as it turns out, for a standing wave. The nodes are going to be where the sine of kx equals 0, or because these are going to be the points where this whole thing here is going to cancel out, and you're going to have y equals 0. Again, y is its transverse up and down, and so the nodes are where the y is 0. And so that's going to take place when the sine of kx is 0. When is that going to happen? It's going to happen at half a wavelength. It's going to happen at a full wavelength. 2 lambda over 2 is basically lambda. It's going to happen at 3/2 a wavelength, and it's going to happen at 4 over 2 is 2. So 2 lambda. That's where the nodes are going to be. So anyway, you could derive that because k equals 2 pi over lambda. And the nodes are going to be at, pi over k is where the nodes are going to be. Because pi over k is where sine of kx is going to equal 0. Anyway, so that's where the nodes are going to be. One last thing. The average rate of energy transfer in this thing is going to be 0. Now, locally, I mean, you do have some energy transfer from node to antinode, and you do have some back and forth energy transfer locally. But when you think about it, the energy that goes down to the fixed end is the same or cancels out with the energy that comes back this direction. And so, on average, the energy transference becomes 0 because you have a precise movement of energy back and forth. And so, energy does not transfer from one end to the other in a standing wave. And the average rate of energy transfer is 0. And there you have it, standing waves.